suppose we have this type of shape. Call it f of x. We're going to bound it from A to B. True or false, we know how to find that area. True. What shape do we make to find the area? And how many rectangles do we end up? An infinite number. Well, we're going to change that just a little bit. Now what we're going to do is we're going to take this shape and we are going to revolve it around the x-axis. Now, when I do this, I've noticed that the hardest part for all of you is being able to visualize what that means to revolve it around the x-axis. You're really taking this shape right here and you're starting to turn it. So it's going to come out towards you, okay? Three-dimensionally. It's going to rotate towards you and down and then back. So you're going to get a solid, a three-dimensional solid. I'll do my best to draw an example. Before you criticize me, I'm going to try to do it. Kind of see what's happening? I'll try again. I'll try it with a rectangle. So what we did is we found the area of a rectangle. But now what we're going to do is we're going to take that rectangle and we're going to spin it around. We're going to sure, funnel would work, but it's solid all the way through. It'd be like if you took a dime and another dime, and then a couple pennies, and then a couple nickels, and then a few quarters, and stacked them all side by side. And you would get a three-dimensional shape. Can you think of something like that? Okay? That's what we're getting. The question is, how do you find the volume of something like that? Well, instead of finding the volume of, or instead of finding the area of a rectangle, I'm going to find the volume of a disc. And so if I take one of those discs, that disc has a very specific radius, and it has a specific width. Somebody want to tell me whether I have horizontal width or whether I have vertical width for this disc? Horizontal width. So the width is dx. In order to find the volume of a disc, I find the area of the circle and multiply it by that dx width. What is the area of a circle? Pi times your radius squared times dx. Now, if I'm working with dx, all the variables should be in terms of x, but I have an r. Let's get rid of that r. As I drew my red disk here, would you agree that that blue segment represents the radius? Can you think of an expression for the radius instead of an r, something that would have an x? F of x. Look, the distance from 0 to this function is f of x. So therefore, we would plug f of x into that radius, and we come up with pi times the function squared dx. How many disks would you like to add up? An infinite number. So therefore, the formula for volume by disks around x-axis. There's a number of ways we can do this. We're going to change a lot of this in the future. We're going to do just very basic examples today. You're going to take pi times your function squared dx bounded from a to b. So the integral is extremely powerful. We can use it to not just calculate area, but we can revolve it and find volume. I want to make a note here that as we cut this, anybody have ham this Sunday? Yesterday, anybody have ham? Okay. If you cut one side of the ham, you're going to get a bigger slice than if you cut the other side of the ham, right? Okay? And so you can think of this almost like slicing a ham. You're going to get all sorts of, thick pieces off of there. And they're not all going to be the same size, right? But relatively speaking, they'll be similar in shape, right? They would all be kind of circular in shape. We know how to find the area of circles. What's kind of cool is it doesn't matter what shape you have as long as you know how to find the area of it. So if we did a cross-section, it was rectangles or pentagons or anything, we could actually do this as well. So let's try a basic example. Find the volume of the area bounded by y equals the root of x equals 4, and x equals 0, rotated around the x-axis. Again, this test is open note. It is not open teacher, but it is open note. And not next week, but the following week. Yes, without a doubt. So, I'm going to draw this shape. Okay. Let's try to figure out first the region that we're rotating. What does the square root of x look like? So I'll draw that. What is x equals 4? What does that graph look like? A vertical line at 4. What does x equals 0 look like? Vertical line right here, and we're going to rotate it around the x-axis, okay? So we're really looking at this region right here. This is the region that we're forming that we're going to rotate around, okay? Now, I'm going to draw the bottom portion of it when I rotate it. And again, what we're truly doing is we're taking a rectangle from that area, and we will spin that rectangle around. And when we spin that rectangle around, what shape do we get? Hint, it starts with a D, a disc. I breathe a sigh of relief because I know how to find the volume of a disc. I take that disc and I'm going to place it over here. You guys, I want you to know that I'm showing the full amount of work today because we're going to make these increasingly more difficult. What I like to do is I like to draw a dashed line for the axis of rotation. And I like to draw another dashed line for the top. Can somebody tell me what is the axis of rotation here? The x-axis, 0, meaning y equals 0. And that's what I'll write, okay? What is used to form the top part of that volume, of that disk? The function y equals the square root of x. Does everybody agree that the distance between those two things is the radius? And if I want to find the distance between two things, I subtract them. Do I do the top minus the bottom or the bottom minus the top? Top minus the bottom. So you just get the square root of x. Now you may be saying, well, what's the big deal? Who cares? It's the square root of x. You could have just written it. It's not always going to rotate around y equals 0. Okay? We could rotate it around y equals negative 3. Or we could rotate it around y equals 5. Or we could rotate around x equals 2. It will change a lot. So keep that in mind. Okay, What is my thickness? Is my thickness dx or is it dy? Dx. So I will now write an expression for that volume. Pi times the radius squared times the width dx. That is the volume of one disk. How many disks would you like to find the volume of? I agree. Let's do an infinite number. So I will integrate. We start collecting these disks at 0, and we go all the way out to 4 as we collect these disks. So 0 to 4, pi, and square root of x squared is just x dx. I set up my integral. You can see that this integral represents the volume of this region. Extremely powerful to be able to use that. Nope, the answer is, what is the antiderivative of x? Pi comes along for the ride. 4 and 0. Plug in 0, what do you get? Okay, so we just have to do 4. Plug in 4, and you get 8 pi. 8 pi is the exact area of that volume. Or exact area of that volume. Just deduct my pay right there. All right, exact volume of that area revolved around the x-axis. Okay. What do you think? Can you do it? And that's the challenge. So, Belle's going to go here. You're going to get some brain food. We'll do examples 2, 3, and 4 when we get back. I have a worksheet for you for an assignment. Example 2, find the volume of the area between y equals x squared plus 1, x equals 0, and x equals 2 rotated around the x-axis. What shape does x squared plus 1 make? Parabola? Who said a line? Holy cow. Try 9th grade again. All right. Yeah, that's a good point. All right, so if I rotate it around the x-axis, and again it's x equals 2, this is kind of the shape you're going to get. Give me an example of something that might look like that once I have a three-dimensional piece to it. Sure, yeah, flower pot, good. Except there's no hole in the middle, right? Sure, yeah. Yep. End of an axe? Oh, okay, I get it. A hammer? Okay. How about a tree stump? Okay. So a tree stump where this is the bottom, this is the top. Bell of an instrument, except it's solid all the way through. Thank you. Excellent. So what we're going to do is we are going to take a rectangle. Does my rectangle have thickness of dx or dy? Dx. So I'm going to rotate that rectangle all the way around. See, when I spin it around, that's the shape I'm going to get. So if we take this disc, you guys said you have thickness of dx. What is the center? Y equals 0. What creates the top of the disc? So you can see, as you look at this, that the radius will be the distance between these two. And if we subtract the top minus the bottom, we get x squared minus or plus 1. Somebody give me an expression for the volume of the disk. pi times x squared plus 120 squared dx. Any questions how I got that? That is the volume of one disk. How many disks would you like? Sound. Think that we said we want an infinite number, and we don't even get worried by that, right? You don't even worry about. All you do is you just grab the integral. I mean, that's so nice. You have to be able to appreciate the calculus there. It's pretty ridiculous. And we go from 0 to what? 2? Do you know how to find that antiderivative? How? Substitution would work if there was an x outside, but there's not an x outside. So in order to do this antiderivative, we must multiply it out. So that will be part of this challenge for you. As if you remember the last unit, we spent a lot of time finding antiderivatives, evaluating these integrals. In this case, we'll go from 0 to 2. We have x to the fourth plus 2x squared plus 1 dx. Equal to pi times x to the fifth over 5, 2x to the third over 3. Plug in the 2, 32 over 5. 2 thirds is 8 times 2 16, 16 thirds. It's 2 over 1. What's the common denominator? 15. Yo. Yeah. Well, because we're going to end up multiplying our result by pi. Whatever we get, we're going to multiply by pi. You can do that as well, but it's not going to make a difference what you distribute it now. Okay. So I multiply top and bottom by 3. I get 96 over 15 plus multiply by 5. Looks like that's 80 over 15. And that would be 30 over 15. And 96 common denominator by. So 96 plus 80 is 176, plus 30 is 206. So 206 pi over 15. 206 is not divisible by 5, nor is it divisible by 3. So it is simplest fraction. Yeah? Isn't it cool to kind of look back at the problem and say, oh, that's what we did today? Are you sure that's other people are like, I had two teachers there walking by when I was kind of getting stuff ready for today's lesson. They're like, that's what killed me. They're like, I can never do that. Like, what are you even doing? No big deal. We're just adding up the volume. Well, remember that we are doing area, but area can represent profit, can represent snow accumulation, it can represent radioactive decay of material. There's a lot of things that are applicable in the real world where the integral applies. Now we're adding a third dimension. So that third dimension could be, say, over a given time interval, for example. So you might be able to find area at one specific time, but then you're going to... There's all sorts of applications. And we'll get to that. We'll get to it. You'll be excited. We'll get back to example 3 in a second because I got to change it. You're going to flip over to example 4, and you're going to try it on your own because you're really smart. Go. again, your ability to graph these shapes is extremely important, okay? And as I look at this graph, a lot of you went to your calculator. If I just simply factor out negative x, I can see that it intercepts at 0 and at 3. So this graph is pretty easy to draw. That's all you need to draw. As you rotate it around the x-axis, you're just going to get a bottom portion like that. You can put your rectangle anywhere on the original portion and rotate it around. You can see the disk that it will create. So could somebody describe for me the shape that we're actually finding the volume of? A ball, for sure, football. Yep. Basically a football. With dx or dy? Dx, x or y equals 0 is my that part, and then the top is y equals negative x squared plus 3. So my axis of rotation is y equals 0, and what forms the top is y equals negative x squared plus 3x. So my radius will be the distance between the two, which again is just a function. So my integral becomes pi, the volume of the disk is pi times negative x squared plus 3x quantity squared dx. So once you have the volume of one of the disks, it's very easy then to make the next step and say, well, let's do an infinite number. 0 to 3 pi negative x squared plus 3x y squared dx. I'm going to have to multiply that out. So we get x to the fourth minus 6x to the third plus 9x squared dx. Antiderivative, x to the fifth over 5 minus 6x to the fourth over 4, or 3x to the fourth over 2. And this would be 3x cubed. We're going to evaluate that at 0 and 3. So we have pi times 3 to the fifth is 243. 3 to the third times 3 will be 3 to the fourth times 3 is 3 to the fifth as well, so 243 again over 2. And then 3 to the third times 3 is 3 to the fourth, which is 81. Common denominator is 10. I'll multiply top and bottom by 2. I got 486. Minus, multiply that by 5. That would be 1,000, 1,200, 1,215. Plus 810. Anybody 486 minus 1290 or 1215 plus 810? Yeah, the 0 came from there, sorry. 81 pi over 10. Just make sure in your final answer. Okay, I think you have seen enough examples where you kind of get the idea, right? So let's just switch the last one up a little bit, and let's rotate it around the y-axis. Okay. So we're going to switch the directions for the last one. We're going to find the volume of the area bounded between y equals 1 half x plus 1, x equals 0, x equals 4, and y equals 3. And we're going to rotate it around the y-axis. So what does the graph of 1 half x plus 1 look like? That's a line that passes through 1 as the slope of 1 half. So up 1 and over 2, up 1 and over 2. We're bounded at 0, 4, y equals 3. Do you see the bounded region that we're actually referring to? The top part. Yep, because it's the y equals 3, so therefore it has to be this area. The bottom would not be bounded by y equals 3. Now I'm going to spin that around the y-axis. Well, I can't draw a vertical rectangle this time. I have to draw a horizontal rectangle. Does that horizontal rectangle have thickness of dx or dy? So thickness is dy. What's the equation for the center of rotation? X equals 0. What forms the outer part of the disk? The function, correct? Which is y equals 1/2 x plus 1. Now, if I have y, if I'm working with dy, all my variables have to have what? Have to have a y. But this has an x. So what should I do? Solve the equation for x so it's in terms of y. So I'll subtract 1. Y minus 1 is equal to 1/2 x. Multiply through by 2, and I get 2y minus 1 is equal to x. So that's what's going to serve as my radius. Notice this time we don't have a top and a bottom. Foot minus 2. Notice that instead of a top and a bottom, I have a right and a left. So if you take the right minus the left, you do get 2y minus 2. So therefore my volume of the disk will be pi times my radius, 2y minus 2, 20 squared dy. So just make sure that if you have a thickness of dy, that you rewrite it so it's in terms of y. I want to integrate this from what? Should my bounds of integration be x values or y values? They should be y values. 1 to 3, yes. Multiply this out. Pi times the integral of 1 to 3 of 4y squared minus 8y. You start at 1. You're going to start collecting discs. And you're going to go all the way up to 3 as the last spot you're going to collect discs. dy. Take the antiderivative. y to the third over 3 minus 8y squared over 2, or 4y squared plus 4y. Because I'm going from 1 to 3 now, I'm going to have to subtract. Actually works out quite well. Plug in 3, you get 3 to the third is 27. Divided by 3 is 9, so you get 36. Minus 4 times 9 is 36. Plug in 1, and you get 4 thirds. Minus 4 plus 4. As you can see, it works out quite well. Your 36's cancel. Your 4's cancel. You get 36 thirds minus 4 thirds is 32 pi over 3. Your final result. Okay? So, you have your notes. I would like to give you a work day tomorrow to practice this. But that's not possible because I'm going to be gone on Wednesday. So we need to move forward tomorrow. And workday Wednesday. 12 is the same as 36 over 3. All right, folks. Have a great day. Day 1 of your last 10 weeks.